Good to see you again. As you can see, I've lost some hair over all these emails that I've been getting, but we're here to do the last new content. And as I said, it's going to be mostly non-computational. We do have to look at graphs and different things like that, but most of the content's going to be idea-based and try to relate to real-world sort of things. So I've got a bunch of key terms and definitions on the screen there. Kind of go through them. I'll show you a little bit of a demonstration using a ruler that will help us get a little bit of idea of this idea of oscillations and frequencies and periods. And then we'll get to a little activity where you're going to have to you're going to have to do a little lab at home. And I'm going to give you some leeway in time on this just because I don't know how much stuff you've got laying around. Normally we would do these with the lab materials in class, but I couldn't check that out to you on Friday the 13th because I didn't know we wouldn't ever see each other again. So anyways, let's go ahead and take a look at what we got there on the screen. So oscillations are a fancy sounding term, but oscillations are things when things go back and forth over and over again. And another term that sometimes gets used for that is vibrations. So oscillatory motion or oscillations are just a fancy way of saying that things essentially obey a sinusoidal graph. If you've seen a sine wave, goes up and down, repeats over time, and when you did all that, algebra 2, pre-calc, whenever you guys do that stuff, the trig functions, you understand these ideas of period and frequency and amplitude, but you kind of forget it until you get back to physics and we talk about it. So we've got oscillation. There's a definition that it's a repetitive motion or cycle that is going around some equilibrium point. This will be demonstrated today when we talk about pendulums. Period is going to be the time it takes to complete one full oscillation. So a couple of things in physics we use the term period for, whether it's the time that it takes a planet to orbit a sun or the time it takes a ball on a string to complete a cycle, to say what's the period of the motion. Well, that just means the time it takes to complete one full cycle around. And with a oscillation, it's the time it takes to go from one extreme that's been moved past an equilibrium point, then it's going to go through the equilibrium to the far end, back to where you release it. That's one oscillation. So in swimming, you can think of it as if you jump off of a platform, get to the far end of the pool, swim back to the platform. That's one period in terms of the way we think of oscillations in physics. Frequency is going to be how often those oscillations happen. It's literally the inverse of period. So we'll get to doing calculations and stuff later on, but period is typically given capital T as the variable, and frequency is a lowercase f. Well, frequency is literally 1 divided by the period. They're just inverses of each other. So where period is the time for one cycle, the frequency is the number of cycles per 1 second. They're inverses. An amplitude is how far an oscillator is moved from its equilibrium point, the place it wants to be. You move it away from there, and then you release it, and it's going to go through some repetitive motion. Well, amplitude is how far away from the equilibrium it's been. So if you think of something like a spring, it's how much you've stretched it or compressed it beyond where it wants to hang out. That was x when we did the Hooke's law equations. And for a pendulum, it's going to really be more the angle that it's displaced away from center. Which brings us to pendulum, which is just a mass on a string that swings back and forth. Nothing too fancy there. If you've ever been on a swing as a kid, which I hope, it's weird that I would ask that question, but when you were on a swing as a kid, you were a pendulum. You were not a passive pendulum because you had someone pushing you, but you were swinging back and forth on the end of something. So you already know what a pendulum is. You just didn't know what it's called. So those terms and definitions, you want to make sure you get those written down and recorded. Simple harmonic motion, however, is the fancy term for this little unit, and as I wrote there on the screen, it's a misnomer that it's simple, because it's not simple. The mathematics that goes into simple harmonic motion is pretty heavy duty. When I took differential equations in college, the opening chapter, the examples they used was simple harmonic motion, which means there is more complicated harmonic motion, which is just beyond anything that you could ever probably do. And well, I know it is for me anyways. But it's a misnomer in that it's not really simple. It's just the most fundamental of the harmonic motions that people approach in physics. You start here. It's the simple one. But while the mathematics isn't necessarily simple, the concepts can be pretty intuitive. It can make sense if you take a look at it. So what I put there is that, not to belittle Calc BC is hard, but the differential equations that are used, or when you do partial derivatives and you try to solve second order partial derivatives and stuff like that, it can get complicated. But the ideas that are most important and that are going to need to be the fundamental ideas that you think of anytime the word oscillate pops up is that simple harmonic motion requires some sort of initial displacement from equilibrium. Something needs to be pulled away from where it wants to be. Second, the greater that displacement, the greater the force on the object trying to create the oscillations. So if it's a spring, if you stretch it farther away from its equilibrium point, the spring force is going to be greater trying to pull it back in. So there's that idea that it doesn't want to be away from equilibrium, wants to be in that middle point. And third, the last one, is the idea that that force that's causing the oscillation always is going to be trying to reduce the displacement. It's always acting opposite of the displacement. It's never going to try to increase the displacement. So those three ideas there together, well, we're not going to, like I said, we're not going to do the equation stuff today, yield what is the fundamental idea for simple harmonic motion, that is the acceleration that an oscillator experiences is going to be equal to negative, and I'm going to use a constant here. I'll go ahead and use B. Negative constant times x, where x is the displacement. So the negative is there to denote that the last point, that it's trying to reduce, it's going opposite. The fact that these two right here are directly related to each other, if you double one, you double the other, that's the second bullet point. And if you're going to have oscillations, you need to have some sort of displacement. That comes in that if x is equal to 0, when you start the problem, nothing's going to happen. If you take a spring and you don't stretch it, you let go, it doesn't vibrate back and forth. So those three key ideas really need to get hammered in before you even approach taking a look at that equation and trying to solve anything from it. We're not even going to get into sines and cosines yet. We will, but what's born out of these three ideas is all the math. So that brings us to the investigation that I want you to do. The investigation that I want you to complete, that I want you to collect data on and analyze a little bit, and then I want you to submit a little bit of a report. And the report's going to be different. Take a look at that in a second here. It'll be fun, trust me. So the investigation is going to involve doing a pendulum. And the pendulum activity is going to require you to acquire some materials. And the string thread that you can use can be anything. I've got a little spool of thread right here. It happens to be dark blue. I got some red over here as well. Had to raid the sewing equipment. Paperclip, standard paperclip's fine, but any sort of small hook that you can put things on and take things off would be all right. And multiple weights. I'm using 3/8" washers. If you have anything that can be used as a weight, that's fine. If you have fishing lures that have a little like clamp-on lead weights, if you have, well, anything. I said string or thread there. If you've got shoelaces and you've got large chunks of metal and you want to scale this up a bit, that's fine. But I'm going to do it with these kind of simple materials that I found laying around. And washers that I bought recently for home maintenance, car maintenance stuff. I happen to have some extras. But the steps are going to be to really take a look at what you think might affect the period of a pendulum. So we're going to take a look at a little video now of just kind of what I mean by trying to fiddle around with the pendulum. All right, so doing a little demonstration here of how a pendulum works. I've got a washer on a paper clip on some string. And the way I want you to test these out, to do this investigation, is to hold it up against a wall. I know that the friction up against a wall can cause a problem, so we're not doing a hardcore science here. But if you give a displacement to your weight and you release it, it should oscillate back and forth. Now, if you want to hold it a little bit away from the wall, you can. You just make sure your fingers are up against the wall because you don't want to have your hands wobble. But if I set it up like this, I'm actually going to turn it around so it's that way. Give it a displacement. If I start the stopwatch when it's at the left side here, and I stop it when it returns to the left, that's a complete oscillation. If I let it go 5 times, then I can time it 5 times. But this is how I'd want you to hold it up against a wall. If you need some help, you get some help doing it, but this is the setup. Release and let it oscillate back and forth. Now, in that video, I've got the string. It's really hard to see because it's kind of dark. Put on a paper clip, and you can set that up however you want. I tied it with a slip knot. If you don't know how to do a slip knot, I don't know, there's the internet, like look it up. And I'm just adding one washer at a time, like this. And if I just hold it like so, right in front of my own face, it should be really easy to see. That's a pendulum. It's swinging back and forth. I'm giving it some displacement from equilibrium. That's where equilibrium would be. It wants to hang out. But if I give it some displacement, I release it, it's got a period. If I start the stopwatch, go, stop. That's one oscillation. It's a start here, go to the other side, and then return. That's one oscillation. So the question is, what do you think affects the pendulum? What variables are there? So just kind of brainstorm up some ideas of which variables could even be manipulated. So give you seconds, or 5 or 10, write some ideas down, pause the video. Once you're done, you've unpaused it, and some of the variables could be, well, the weight. So I've got a washer here. I said to get multiple washers. Makes sense that maybe you want to try 2, 3, 4, or whatever weights you're using. So the weight, the actual mass that's on there could be a variable. There is, you got a length of string. Maybe the length of the string is a variable. If I have it at one length with a single washer, I let it go. What if I make it longer? Or what if I make it shorter? Does that affect the period it takes to go back and forth? The amplitude. So if I've got it here and I release it from a small amplitude versus from a big amplitude, does that affect the time it takes to go back and forth? So these are a few variables. Am I leaving anything out there? The type of materials, we're not going to worry about that. But the steps I want you to follow are to make prediction as to whether you think those variables will affect it. So the mass that's hanging on there, you think it's a direct or inverse relationship? If you think you increase the mass, the period will increase or decrease or stay the same. The length of the string, same idea, as well as the amplitude, the angle that you pull it out. And we're looking for dramatic changes here. Like if you got a stopwatch and you say, oh, the period was 1 second, and then I did it again with changing this variable and I got 1.05. Clearly that's, I doubled this variable and I got 0.05 seconds. No, that's not a big change. We're looking for the idea being that if you make a significant change to the length, the amplitude, the mass, that you're going to see a significant change in the time it takes to repeat a cycle. So no significant change, you can probably say that there's no relationship there. So you want to change one variable at a time. So mass, length, amplitude, just change one, keep everything else as close to the same as possible, and then record the time. You want to just kind of write it down on paper. I'm saying to do 5 oscillations. So start it, set the timer to go, it goes over, back, over, back. So every time it returns to where you let it go is 1 oscillation. Do time 5 of those and then divide by 5. Then make a change, time 5, divide by 5, and keep doing that. Build a little table, and that table could look something like this. So we could have, let's say, length, and you could have, I don't know, you could actually measure it out. You could say like, oh, what if it's 5 inches long, 10 inches long, 15 inches long, make those adjustments, and then you can calculate what the period is for each of those things and see if it changes. You could also do that with the mass, except here you might do like the number of things. So it could be like 1 washer, 2 washers, 3 washers, and then again, measure the period and so on. Now, the way I want you to turn this in is instead of doing a Google Doc, because I've actually seen enough Google Docs as well for a while, I wanted you to do it as a short Flipgrid video. Flipgrid videos, if you've never done them before, there's an app you can download on your phone, but you can also just shoot a video on your phone and get it onto your computer and upload through the website, through Canvas. If you have a school email account, you already can create a Flipgrid account. If you access the Flipgrid assignment, it's going to be called Pendulum Investigation. If you access that through the Canvas assignment, you're automatically connected using your Canvas account, and you upload the video there and I'll be able to watch it. I think I have it set that I have to approve them before everybody else sees them, double check that, but other people can see them as well and kind of get a gist for what's going on. But I want you to create that little short video, minute to 2 minutes, where you show me the demonstration once. So if you've concluded that a variable affects the period, I want you to show me you doing the demonstration with the pendulum going, adjust that one variable and show how the period has changed. Just give me a live demo of that, and then nice close-up of your data that you recorded, like little tables there. And then you submit it, and then you're done with it. So we'll take a look at all the mathematical calculations, and we'll take a look at all of the ways you can manipulate graphs and everything like that later. But for an introductory activity for pendulums and oscillations, I think this is pretty good. So let me know if you have questions, and I'll see you later.